Okay, so good afternoon everyone. I'm Pete Wilkins from DCU and presenting this work done in collaboration with Graham and there's Graham and Alan. So our interest in this project was that this whole field of brain-computer interface is obviously rapidly expanding and there's a lot of specialist hardware. And we wanted basically to see what could we do with some really cheap commodity hardware. In this case, the stuff we got cost approximately about $1,100 US. So very accessible, very cheap hardware. So to give a brief overview of the talk, I'll briefly go through the apparatus we used, then our experimental methodology, followed by the outcomes of our experiments and some conclusions. Again, this is just the rough overview, so I mean, we can go into more detail afterwards if people are interested. So the equipment we used, it was a device known as the Pendant EEG. I'm not sure if anyone's come across this. It is a 2-channel device which can take 254 samples per second with a 12-bit resolution. It's a wireless device that has a USB dongle and it is 2 nodes. So what we did was we bought 2 of these devices and we effectively daisy chained them together to give us 4 nodes. Because this was commodity or a consumer device, I should say, really, the software that came with it wasn't really appropriate for the application we had in mind here, so we actually ended up writing our custom drivers and software to actually process the signal. So to give you some idea of the devices, that's the 2 of them up there, and you can see in the next room, and down the bottom left there's a credit card sized object to give you some sort of idea of the scale of the wireless transmitter. So that just clips on the back of the subject's back, so it's fairly inobtrusive. Because of our 4-node setup, we got some advice on where to place the nodes, predominantly around the PZ site. That picture of the back of my head is slightly off because those 2, P3 and P4, should be further down, but that was an early picture. But that's where we're locating our node placement. So our methodology, because we only had 4 nodes, we effectively tried to dig down into as much data as we could get from each of those nodes. So we conducted a bandpass on each signal. We also conducted a fast Fourier transform and further sampling. In effect, this gave us 24 features per channel. With 4 channels in, that was 96. And each of the offsets you see there was from the presentation time of the stimulus. So broadly, we had 3 major classes of experiment. There were a few other ones we did, but we'll just go through these ones briefly now. The first one, reliability versus speed, was really to detect with our 4-node setup how fast a presentation could we get with aggregate classification in an oddball experiment. So that data set utilized those beach rocks, and we had 4 subjects for that with time range from 500 milliseconds through to 50. The second experiment utilized that data that Christos just showed of those colored heat maps, for want of a better term. This, you could almost argue, is like a non-binary classification task where there's actually 3 classes of targets, where we had the genuine oddball, the non-obvious oddball, and the non-oddball. In this case we had 6 subjects, with one of the subjects being from here in ACT, who should actually, in theory, have provided us with a different signal response to the data because they were very familiar with the data. So that's where the expert versus non-experts component comes in. It was also to kind of examine how did that expert subject vary to the other subjects, which were lay people in our university. Finally, the experiment we had there is a SenseCan, and I'll have a slide on this later. That's an area of research that our group in Dublin does. The SenseCan, to summarize very briefly, is a wearable camera, and it takes a visual diary of your day, taking images every couple of seconds. So it's a very personal data set that relates to the person wearing it. And effectively what we're doing in this experiment was comparing, if you showed images from the person wearing the device, how did that vary to someone else looking at those images? And what sort of difference may you observe? And actually this is the slide here. So you can see the SenseCan down there in the bottom left. That is worn around the person's neck and just sits there. And that takes in the region of about 2,000 images a day. So, you know, in our research group, we do a lot of multimedia stuff, so we would do things like trying to segment those images into homogeneous blocks and those sort of things. But it provided an interesting data set that was a sort of corollary to the previous data set that Christos explained. So our evaluation criteria, we were looking at grand averages from the ERPs just to determine if we were actually, observing any difference in the waves. And then we also went into the creation of some discriminative classification, specifically SVMs, when using the metrics of ROC graphs and AUC. So into reliability versus speed, on the left-hand side there we can see 1,000 millisecond presentation time, and we can see a quite clear differentiation between the signals there. So the solid line is the non-oddball, the dashed line is the oddball. And with the 4-node setup, and actually this is only taken from PZ, sorry, so this is a 1-node extraction, we get a clear separation. For 50 milliseconds, we've obviously getting a lot more stimulus events occurring in the time window we're looking at across the second, but we can still see a separation in the signal. So this is a graph that ESA did up on our data, which is pretty nice. So the red line there, as you know, is random. So the convex curves going away is our classification performance, and the further away the better it is. And what we can see here is a nice stratification occurring from 50 milliseconds up to 500, which was nice to see because it meant that whatever signal processing techniques and classification approaches were yielding decent results, because that's the sort of effect we'd like to see. There is some issues there with 500 and 300 about them being close. We would like to see 500 out a bit further, but that's a separate issue which I can discuss if people are interested. Into the next set of experiments, this expert versus non-expert with the 3 classes of oddball that was being discussed. Of the 6 subjects that were used, the expert and 2 of the non-experts were actually able to distinguish 3 classes based upon an examination of the grand averages once we completed those. If we actually looked at those 3 subjects, we were getting classification accuracy around 0.61 to 0.64 AUC, whereas for the remaining 3 subjects, there was no distinction there, so it was effectively no classification possible. So this is a visualization of the grand averages for the expert user. In the top graph there, we aggregated the non-obvious oddballs and the oddballs into the one class, and that's the dashed line. So the solid line is a non-oddball and the dashed line is the oddball. In the bottom graph, that is a graph of the 2 oddball type events. So the dashed line is the obvious oddball and the solid line is the non-obvious oddball. So you can see there from the grand average that there is actually some distinction in the case of the expert. Finally, for the SenseCan experiments, and we're happy to discuss these later, these proved more difficult than anticipated for us, and we think this may have been an artifact of only having the 4 nodes, because the experiment we actually had, which I didn't describe before, was the oddballs in that data set were shots of people eating. So if someone saw someone eating, hopefully would elicit a P3 response. However, the problem with that is that, typically when someone's eating, you're also going to see their face. So when we built the classifier, we didn't know whether we're actually detecting the oddball event or whether it was the face recognition that was being triggered off, or that sort of thing. So a few more nodes might be more helpful to help try and help that separation. So in conclusion, we did find that the 4-node setup was capable of conducting this oddball style experiment, certainly with the moon rocks and that sort of data set. We got good performance around 300 milliseconds. We did find the generation of data for classification required fairly careful parameter selection. The one thing I haven't mentioned actually was that in the creation of our models, the models were specific to each subject. So we weren't able to create one generalized model with the data available. Which perhaps again there is an artifact of the data we had available. The third point there, from the grand averages, it looks like it's theoretically possible to try and separate these oddball detections between expert and non-expert user. However, obviously it needs a lot more further work, but the indications are interesting. And that we did find great variability between subjects. So in the long term, if we stick with the 4-node setup, we need to find a way of generalizing our approaches to actually work across multiple subjects rather than having specific models each time. And that's the talk.